Hello, everyone. When we're talking about energy, one of the things that we need to talk about is when we're comparing, say, mechanical devices like this nice four-cycle internal combustion engine. And when we compare engines to one another, we often don't want to know just how much energy they can output. Because after all, even a small engine, over enough time, can output a great deal of energy. So instead, when we compare one machine to another, we're often trying to compare how quickly they can transfer energy. Right? How quickly they can transfer energy maybe from chemical potential energy into kinetic energy, as with an internal combustion engine. That quantity is what we defined last year as power. Right? Power is the rate of doing work. And remember here, work is a loaded term. Work is the transfer of energy into or out of a system by means of an external force. So we're talking about how quickly we are transferring energy from one thing to the other. So this, of course, leads us directly to the equation that we developed last year. Power is simply work over time, but that's for constant external forces. We'll get a little more complex this year and deal with non-constant external forces momentarily. Remember here, work is the external force times the distance times the cosine of the angle in between. That's if we're using constant forces. Units for power come right from the equation. Work is an amount of energy transferred and therefore is in joules, while time is in seconds. Now, joules per second are a useful enough combination that it's given its very own special name, named after a physicist by the name of James Watt. So 1 joule per second of energy transferred is 1 watt of power. So a 60-watt light bulb is transferring energy at 60 joules every second. And a 120-watt light bulb is transferring energy twice as quickly, 120 watts every second. Now, you'll rarely see internal combustion engines like this one done in watts. Usually electric motors might be in watts, like your hairdryer or something like that. But an internal combustion engine is probably going to be in something a little bit more complex, which is called horsepower. You might remember from last year that 1 horsepower is roughly 746 watts. And it was a unit developed by James Watt in order to compare horses to steam engines. And so 1 horsepower is literally supposed to be the power output of a typical horse. So supposedly a typical horse can transfer 746 joules of energy every second. Now, as you'll see, of course, in the packet that you're going to work on, there's ways of calculating power, and very often the difficulty in power is calculating the work. That's usually the tough thing, but once you calculate the work, then the power becomes quite straightforward. But we are also going to use the one little variation we developed last year, which makes a great AP multiple choice question. Let's say we have constant one-dimensional external forces. Then power is simply work divided by time, the rate of doing work. But if work is the external force times the distance times the cosine of the angle in between, and if we assume here a one-dimensional force, that means theta is 0 because the force and the displacement are in the same direction. And the cosine of 0 is, of course, 1. So we end up with an equation we could write as external force times distance over time. Now, why did I write it that way? Well, because hopefully distance over time is setting off bells in your head. Distance over time is what we defined way back in the toy car lab as constant speed. Right? Constant speed is distance over time. And therefore, we make a little substitution, and we get the handy power equals force times speed. Now, this equation, again, is a great little multiple choice question because if you know the equation, it's a fairly simple thing to do. Hey, there's a force on this object of this many newtons. It's moving at this speed in meters per second, so that's a newton meter over a second, or a joule per second, or a watt of power. And if you know the equation, you're done. Right? You don't know the equation, probably going to be hard to do. So not a bad one to learn. And again, this is for constant one-dimensional forces. Now, we do have an alternate version of this. Well, really, it's a more complex version. If power is the rate of doing work, then using the calculus, we can say power is the derivative of the work with respect to time. Because remember, a derivative is a slope. It is a rate of change. Right? So a derivative of the work function with respect to time. So this would be in a case where maybe they give you the work as a function of time instead of a function of distance, which is kind of a weird way to do it. But if they did, then you could take a derivative and evaluate it and figure out the power output of something. Remember here, if we do a constant one-dimensional force, this would be the derivative of the external force times x. We're doing one dimension here, cosine of theta. And in one dimension, theta is 0, cosine of 0 is 1. So we have the derivative of the external force times the distance x all over, or with respect to time, sorry. And if it's a constant force, we can pull it outside of the derivative. And so we get external force times the derivative of the position with respect to time, which of course we know as the velocity. So we get the same equation again. Whether we look at it in a calculus way, as we are up here, we still end up with the same equation down here. Again, a handy version when you have the force and the speed of an object and they're in the same direction so that you don't have to worry about the cosine at all. So this is really a one-dimensional kind of case. And then you can use this equation and very simply do a multiple choice problem. Hope you enjoyed this quick little review of power.